Well, what have we got here? Lots of applications of triangle measurement or trigonometry. Have a look up the top here at these two. Something to do with the Cartesian plane and angles between the lines and the x-axis. And what about this into astronomy? What's the diameter of the moon? Maybe we could work it out with a figure like this. And if you're a fisherman or sailing, America's Cup and all that stuff, I hear New Zealand's going to win it this year, here's a little problem for you. Let's not hit that cliff, let's look up at the lighthouse. And then a 3D problem. If you're on the inside of a pyramid, don't know how you'd get there, but anyway, inside of a pyramid you might want to be doing some measurement of heights in there. So all these sorts of problems are mentioned in this new syllabus as applications of trigonometry. So this is going to be quite exciting. So let's go down and look at the first of them. And the first of them is to do with this Cartesian coordinate system, and we've got a straight line here. And if you remember, a straight line has a formula in one form, y equals mx plus c, called the slope-intercept form. So m is the coefficient of x, it's the slope. I wonder if you can explain why that is the slope, that coefficient of x there. How does that work? And the c value down the end is the y-intercept. So let's check it out for this line over here. Yeah, we'll come down the y-intercept over on this side. When x is 0, y is -1. That works. And the slope is a half. Let's have a look here. I've got the equation of the slope, or formula for slope, y step on x step if you like, and that in this case comes to 1 over 2. That means if you move 2 in the x, it's going to have a y movement of 1. Come over and check it out over on the diagram here. And so there we have a positive movement of 2 in the x and resulting in a move up in the y. So if we go to any point on the line, move across 2 in the x and 1 in the y, we'll get another point lining up. So just remembering the equation up here of a line is the rule which the points must obey to form that line. Okay, to line up if you want. Line up, so you get linear functions that plot as straight lines. Okay, so there's a lot of interesting things there, but what are we interested in really? Hang on, let's tidy this up. What we're interested in is this angle that any straight line makes with the positive direction of the x-axis. So we're talking about that angle, not this obtuse angle. Okay, so can you look in this right angle triangle, and if you look at it, here's our angle theta here, angle theta, and the tangent is the opposite over the adjacent. The tan of theta, let's put it over here, the tan of theta is a half. Hey, hang on, but that was the slope. So the tangent of the angle that the line makes with the positive direction of the x-axis is equal to the slope. So we could find the angle back over here now. Inverse tan, or the angle is tan -1 of m, or put in m as a half, and you can get 26.6 degrees, approximately 3 significant figures, and making sure that your calculator is set up in degs, degrees, not rads, radians. Now that's an interesting application of triangle measurement or trigonometry. Okay, can we develop it further? Let's have a look at another case. What about if the line has a slope going the other way, a negative slope? Okay, so let's come down here a bit. Look at this. This has got a slope of -1/2. So that means, now I disagree with the way Pearsons have got this here. I think the best way of thinking of the slope is the y step, or y2 take y1, or delta y on delta x. That, we agree on that. And if that is equal to -1/2, I think it's best to call that -1 over 2 and take it as moving 2 in the x results in a -1 move in the y. Okay, so let's check that. So if we talk about, instead of neg 2, let's start at this point and move plus 2 to there. What happens? We drop by, so let's go down by neg 1. I'm thinking of y here as the dependent variable and x as the independent. So we think about positive movement in the x resulting in a negative 1 movement in the y in response, or dependent upon the x. Is it still true? Let's have a look. The angle here this time would be this angle. As the line comes through, the angle whose tangent is still the slope is this one. Y step over x step. So tan neg 1 of m, or tan neg 1 of a half, neg a half, is neg 22.6. Now it's in a symmetrical position. Hang on, we'll just go back here. In a symmetrical position to the one going the other way. I'll just correct that here. So if we look at that coming through here, symmetrical position, that was y equals a half x plus 1 there. Okay, so it's the same idea. Can you note if the angle between the line and the x-axis is going to have a tangent of m, it's got to be with the positive direction of the x-axis, this side, and not the other side. Okay, let's develop it a bit more to do something a bit more interesting. And here we're going to summarise that for a start. If you have a line with a y-intercept of naught c, making an angle of theta with the positive direction, that's on the right-hand side of the line, and that we're going to talk about an angle from neg 90 to 90, an acute angle, then the slope of the gradient, or slope or gradient of the line, is the tangent of that angle. Okay, or you could think of the line as not mx plus c, but tan theta x plus c, where the angle theta is the angle it makes with the positive direction of the x-axis. All right, an interesting result explicitly mentioned in the syllabus, in this new syllabus, First Examinations 2014. So let's have a look now at another example. Let's see if we can find an angle between two lines. This would be interesting. Let's draw the line y equals 3x and the line equal y equals neg x. Now we can find the angle that y equals 3x makes with the x-axis. There it is there. That's alpha. And that's tan neg 1 of its slope. There's an angle. Let's do the same thing with the angle y equals neg x makes with the positive direction. That's that angle there. And that's tan neg 1 of its slope, which is neg 1. So that's neg 45 degrees. Okay, so the difference between them is one angle alpha take beta, which effectively adds up to 117 degrees. There. Okay, but what we usually give is the acute angle. So here, that is the big angle there, approximately 117 degrees to the nearest degree, or to three significant figures, and the other one is 63 degrees. So we're going to quote the acute angle between the lines, because it says up here the acute angle, but the convention in this sort of work, the convention implies we will find the acute angle. Note, it's not a bad idea to draw a diagram rather than just rely on calculation. So draw a diagram when you're trying to do this. This is a powerful little result now, isn't it? Let's have a look at developing it. Here's another one. Find the acute angle here between the lines y equals 5x take 2 and a third x take 1. Right, 5x take 2 is a fairly steep dude, going through at neg 2, slope of 5, and y equals a third x take 1, going through at neg 1 with a slope of neg a third here, a less steep line. Okay, well, first of all, the easiest way here of looking at this is to go down to their point of intersection, there it is there, and to draw a horizontal line. Okay, so the angle at this point that 5x take 2 makes with this horizontal line, it will be equivalent to the angle it makes with the x-axis, won't it? Because this horizontal line is parallel to the x-axis. So what is the angle 5x take 2 makes with that line? Let's call it alpha. There it is in there, alpha. So that's tan neg 1 of the slope, we'll say 78.6, and beta in this case is tan neg 1 of a third, which is that. But have a look now, the actual angle between the lines is the difference between the two. This is alpha take beta, big one minus small one, which is approximately 60.3. Approximately because we're rounding off there, that's the approximate sign, rounding off, and we're going to quote, usually you put this in brackets, to 3 significant figures. Good stuff. Very interesting if you're looking at plotting the paths of 2 yachts on a grid system. Then this would be handy to find the angle between their paths and looking at collisions and things like that. Okay, well, here's our summary. If they are non-vertical lines with equations of that and that, in other words, 2 different slopes, 2 different y-intercepts, the angle between the 2 lines is the inverse tan of the first one minus the inverse tan of the second. This angle may be acute or obtuse. So you can just tan neg 1 both of them and take them away. I think rather than just use this rule in a monkey see, monkey do copying approach, a diagram, a rough diagram would be useful. Okay, just to see what you're doing there. We know the angle is given by, or the tan of the angle is equal to the slope. But just keep your wits about you about what's happening. It'd be good to draw a small diagram. Okay, so let's have another look at one of these. And here we have find the exact equation of line L1, pass through the origin and makes an angle of neg 60. Okay, so C value is 0. And what's mx plus c? Well, we could use this form, y equals tan theta x, remembering that m is equal to the tan of theta. Okay, so what's the angle that it makes with the axis? It's neg 60 now. 120 if you go that way, but neg 60 from the positive direction down to that line. So what's the tan of neg 60? Well, you know the sine over the cos, and therefore it's neg root 3. Now remember, you're expected to know sine and cosine, but not tan, so you work out tan as sine over cosine. So it's neg root 3x plus the y-intercept, of course, is 0. Alright, now what about given another line, 7x plus y plus 1 equals 0. Now you have to rearrange it so you can pluck out the slope. So subtracting 7x from both sides, subtracting 1 from both sides, you get this rearrangement. Okay, so you could just use the formula. The angle between them is the inverse tan of the first one, the angle the first one makes with the x-axis, minus the angle that the second one makes with the x-axis. And this is an absolute value or modulus sign. Means make the answer positive, if you like, absolute value or modulus of a number. Okay, so it's saying at the end we want a positive answer. So we'll take the 2 angles away, and if the answer is negative, it means you've done the other way round, and then you just take the size of it there. Okay, so let's look at what we're doing down here. I draw a diagram as I said before. This is neg 7x take 1. Where are we here? Neg 7x take 1 is that one, and the other one was equal to neg root 3x. So that's that one, and they are intersecting at this point. Then if you find the angle that each line makes with that horizontal line, which is equivalent angle to the x-axis, then you'll have neg 60, and the other angle was neg 81 0.87, that big one around there. The angle between them, that's the angle theta. Take the 2 away and make it a positive. Okay, so do you want to have a look? We'll go down and see how you might do that on the calculator, that absolute value. And here it is here. I don't think it's actually necessary, because you can actually do it by hand and then make the answer positive at the end. But I'll just show you. If you go into run mode, and then in run mode, if you were to hit options there, you can go to calc by hitting F4, and if you go to hang on, no, not calc, sorry, if you hit options, then you will come up with these options, and you want to go to the next window, and on the next window you will see the possibility of abs there, absolute value. So hitting F1, and if you hit F1, this is what comes up. That sign means the absolute value, or making the number positive, if you like. And then into that sign you can enter your expression, and it will give you a positive answer. It's just bringing up the idea that options on the calculator will produce a series of calculations, calculating modes, and one of those is absolute value if you look under number. So options, then number, and or options, go to the next window and find absolute value. Alright, okay, so you could do that. Probably most people would just do the calculation. Just come up here and I'll show you. Most people would do this calculation in run mode, just that one, minus that one, which is that one, and by hand remove that absolute value sign, or make the answer positive. There's no actual need to use the calculator for absolute value. Alright, come down and let's have a look at giving you a go at all of these. Got some diagrams, they're very helpful. So I'll go through these problems, leave you to pause them, and the solutions to these are right underneath. This time, Pearson's, I've taken screen clippings again from Pearson's, and I've split the problems into the 3 different main application areas. So the first section with its solutions underneath has to do with intersecting lines and angles between lines and the x-axis. Okay, so have a go at those. Come down now, and we have the next set, all related this down to question 10 from this set in chapter 7, and let's now look at the answers to those. Please note here, you're going to have to find your own equation of the line. Okay, try to remember that before going on and finding the angle it makes with the x-axis. A bit of revision there. And there's a couple of ways, aren't there? Y equals mx plus c, and substitute the m value in, or y take the y coordinate of a known point over on the line, over x take the x coordinate of a known point, equals the slope, where you'll know a point on the line and you'll be able to calculate the slope between the 2 points using y2 take y1 on x2 take x1. So either way, you should be able to find the equations in 5, 6 and 7, and then find the angles. Let's come down and look at the solutions now. So here we go. This is 7.5 from Pearson's. There's question 1 to 5. The solutions there. And then let's have a look at question 6 to 10. Let's see if we can get them in, I think. Yeah, so question 6 to 10, just checking their calculation, we're looking at the calculation of the slope and so on first of all. Alright, well, that's one interesting application. I don't think you would have ever thought we'd use trigonometry in the Cartesian system, but we can. Let's look at another one. A little bit of an application to planar figures. So this is further applications, and here's the one I had in the leading entry to this presentation, the sailing problem, where we're looking down from a lighthouse, and can we calculate, for example, the height of the lighthouse and things like that. So let's read the problem. The boats are 500 metres apart, so the first thing down here, make sure it's on the diagram. Lighthouse is on top of a 470 metre cliff. It's 470 to there. That's good. Angle of depression from the lighthouse, from the top of the lighthouse, where people stand and look out there, is 40 degrees and 25. Of J and K respectively. So J is 25 degrees, so that's boat J, and K is 40 degrees, so that's a bigger angle to look down. Just remember that angle of depression is the angle from the horizontal. Okay, so we've got all that information, but what we want is H. And actually little h doesn't occur in any triangle. So that's our dilemma here. So let's see how we will go about doing that. And I think you probably already have some ideas. First of all, you can extract the triangle JKT, which is this one here. Pull that out and let's have a look at that and see if we can get some information from it. This is what I call a go-between problem. You'll go between calculations in two different triangles. So what we're going to do is do something over here in this one, I think something to do with this, and then find something in this one, a go-between problem. So coming down here, put all the information we know. So we know this is 25, why? That is alternate angles here. And what else do we know? Well, one was 25 and one was 40, so the gap is 15. Oh, we actually know quite a bit. We knew that one, but we have to be a bit tricky-dicky here. That was 25. The big angle of depression was 14, making 15. And also, with the horizontal, then we've got alternate angles here and here. So we actually have a lot more than what we thought. Okay, so what might we do? Well, you see it's a go-between problem, so we can now actually find KT and use it in the next triangle. When the next triangle, oh, that's the one with the lighthouse in it. Okay, and that's the lighthouse. So if we then find all of that and take away the 470, we're in with a chance here. Okay, so let's find this from this other triangle going between the two. So what will we do? I think we would write this the other way up, wouldn't we? We want a side, so write the sine rule as KT over sine 25. Put the unknown in the top so we don't have to do any rearrangement. KT on sine 25 is 500 on sine 15. Now, KT has been divided by sine 25. Take KT back again. Let's multiply by the sine of 25. And it's easier to evaluate an unknown if it's in the top line of a fraction. Okay, so this is approximately 1816.436 metres. Don't round it until the end of the problem, because we're not at the end. We have to take off the, we have to now use it in this triangle and then go to the lighthouse and so on. So the lighthouse was this bit here, and then it was 470 down here. So let's find the whole thing, and if possible, we'll use Sokotoa. It's a right angle triangle. That's easier than either the sine rule or the cosine rule. So what have we got here? Look out. Yes, we want the opposite. We want that total height. Call it BT here. And what have we got? We've got the hypotenuse. So that's the sine of 40 is opposite over the hypotenuse. Multiplying across by that, we get that. Subtracting 470, which was the height of the cliff here. We said that before. Then we've got 54.795. Round it to three significant figures. And usually you put that in brackets, show what we've done. So that's an interesting go-between problem, going between triangles to solve for one of the unknowns. Okay, getting interested? Well, let's keep going. Remembering, we try to use Sokotoa before anything else because it's the easiest rule, if we've got that right angle triangle. Hey, this is an interesting problem. As viewed from the surface of the Earth, the angle subtended by the full moon is 0.582 degrees. Okay, so that's that angle there. If you spotted it, looked above and below it, you would get that. The distance from the Earth's surface to the Moon's surface is approximately 383,500 kilometres. Find the radius of the Moon to 3 significant figures. Is that possible? Well, we're trying to find the radius of the Moon. Alright, so in this problem, do you realise that the angle between the tangent and the line drawn from the centre to the point of contact, so that CD, that radius, the angle there is 90. That's a theorem. The angle between a tangent and a chord at the point of contact, not a chord, a tangent and line from the centre at the point of contact is 90 degrees. So this one will be 90 as well. Okay, do we have enough? Now, they've got it here, the radius of a circle drawn to a point of tangency will be perpendicular tangent line. So we've got a right angle triangle. Oh, Sokotoa to the rescue. That's good. And therefore, let's pluck out one of those. Let's pluck out the top one. So there'll be symmetry here. Remember, there is another theorem about tangents. Tangents drawn from a common point are symmetrically placed. They make the same angle in here as each other. So therefore, if we halve that angle, each one would be 0.2591. This distance would be there, and what can we do? We can find the radius, I think. Let's go down and use Sokotoa here, because we've got an angle, look opposite. Yep, we want the radius. We've got the hypotenuse, so let's go back up here. The sine is opposite over hypotenuse. So the sine of that little angle is r over, now, that was the distance to the Moon's surface, so the hypotenuse is actually 383,500 plus r. So that's a little bit of a trick there. So multiplying across by r, they've done a few things here in going from here to here. We've got the sine of this, okay, multiplying across by 383,500 plus r equals r. And then we've got sine 0.2591. Oh, well, then from here on it's the same, isn't it? They've done it in a slightly different order. Put it on the other side. So now we've got 383,500 times the sine plus r times the sine. A lot of work here. So getting the r's all on one side, subtracting this r term from both sides. We've isolated the number, then factorising. R outside of 1 take sine of that equals this answer. And what you got there for R will be, it's been times by this factor here. To get R back again, you'll divide by that. Fairly lengthy calculation there, but to 3 significant figures, the approximate radius of the Moon is 1,740 kilometres. What a good problem! Okay, it just shows you that even with the rather simple result of Sokotoa in a right angle triangle, you can do some powerful calculations. Okay, what else can we do? Well, let's have a look at this one. This is a bearing problem, navigation, things like that. The diagram shows a point P that is 10 kilometres, here it is, 10 kilometres south of a point D. A straight line PQ, so here it is up here, straight line PQ, is such that the bearing of Q from P is 45. Now, of Q from, now key word here is from P. So you go to P and you start your measurement, because there's a bearing of Q from P, measured from P. Now just remember, compass bearings are measured clockwise from north, at P, because it said from P. So you've got to be at P, so that's going to be 45 degrees. A and B are 2 points on this road, so here we've got A and B are 2 points. Find the bearing of B, here B, from D, approximated to 3 significant figures. Okay, of B from D. From means you've got to go there and measure theta is the one that you want. Okay. Alright, so what do we know? Let's take the triangle out and see if we can solve for it. Okay, so the triangle that we know is 10, and this is 8. Now, why is that? Triangle PDB, ADB, sorry, is isosceles. Let's look back up at that. Triangle ADB is isosceles. Okay, now why is that the case? Can you see that? They're both 8 kilometres from D. It says though there, should have underlined that. So both 8 kilometres from D. So that's isosceles. So that's going to help us, because what we're going to be able to say is that 2 base angles are equal, and the sum of angles ADB is 180, so we can solve for angle ADB. We haven't drawn that, so I think here, let's go back down here. So ADB, we're saying these two are going to be equal. Okay, so if we can work with those, that's going to lead us on to the answer there. So let's have a look then. We can solve for ADB, using sum of angles. We can solve for DAP because it's supplementary to DAB, and then we can find the third angle in triangle APD. We better do some work before we get too far advanced here. Okay, since theta plus ADB plus ADP is 180, we can solve for theta. Okay, that's the last point. So let's do some calculations. So first of all, the sine of angle DBP, so this angle here, so we can go next to it and get the next one. Sine of angle DBP, unknown, over 10, is the sine of 45 over 8. So this is the sine rule. And then the sine of that will be multiplying across by 10, will be 62.11 degrees. We can do that bit. Now, what have we got? Well, we've got this 62.11, but what are we going to say here? PAD there in that top triangle, are you up with it here? It could be 62.11. Okay, we've got 117.89 there. Where did that come from? That's a supplementary angle to this one. We've used the sine rule, but we can see it's greater than 90, and so up here it could be 117.89 degrees also. And so that's what we're saying here. Looking at that, we've got that scenario. So angle DAB, okay, angle DAB, okay, coming over here, DAB equals DBP, so they were both equal in isosceles triangles, so those two are that. And then here, therefore this angle ADB is 180 minus, that's sum of angles of a triangle, so we should put some reasons here. Isosceles triangle, sum angles of a triangle, and then angle PAD, let's go back a bit over there, angle PAD, here it is here, PAD, 180, well, we've already covered that. We talked about that before. So we'll just get this right now, coming down. So, therefore, ADP, let's go back to our diagram, it's getting a bit messy there. So, it's coming across here. So, our original diagram, we had 17.11. Let's go up a bit here. Go up a bit. Not going well here. I'll just go up here. So going back now, ADP, was 17.11, and therefore we've got this angle, and if we take it away from 180, we've got 107.11 degrees. Now that's a bit messy here. We've just try and look at that again. So what we actually were doing there, up and down here. So can you see that from the first diagram, it's a pity with this sort of podcast here that we didn't have the original figure next to us, could have redrawn that as well. But let's have a look at what we've actually been doing. We're starting off by saying, well, these two were equal. Coming in to this triangle, we could find A, okay, but it was the obtuse angle. So then this one was 62 point something or other or whatever. So this was 62.11, and we said this was 180 minus that. Sum of angles in this triangle, we could get that. Sum of angles in this triangle, we get that. And all that was 180, so we could get theta. That's the journey we've been on, going around and around. It gets a bit confusing when you can't see the original figure when we've pulled it all apart. Okay, but that's the idea now with that. So that's definitely a go-between problem. We're going between a couple of triangles, a couple of different ways. Now just remember, compass bearings are measured clockwise from north. So this is a bearing, always draw in the north sign, north direction, and measure clockwise. Hopefully you've seen some of that before. Let's give you some to do here. So I'll just bring this over again to there, and got a couple of problems there, 11 and 12. Have a go at those. Coming down then, 13. Now these are all the problems related to the planar applications, just in 2 dimensions. 14, 15 and 16, and 17. So have a go at each of those. I'll show you the solutions before we go on to 3D problems. Let's have a look at the solutions. So I'll just bring this across now. Bit enlarged there. 11. That's 13 there. What happened to 12? Did we have 12? Hang on. Oh, it looks like we've left out 12 there. There's 13. 14. Or some of it. There's the rest of 14. 15. Part of 16. Okay, and 17. Okay, having a look at 17 there. Okay, let's go on to some of the 3D problems. It's an exciting section, this. It's impressive what you can do when you've got all those rules available to you now, SOHCAHTOA, Sine Rule and Cosine Rule. You should always try to use SOHCAHTOA first because that's the easiest one to apply, but you need the 90. That's the problem. Okay, come down and let's look at three-dimensional problems now. And just come across here. Okay, so here's a three-dimensional problem. You've got to look at it as a sort of isometric drawing here. It's a vertical pole supported by 2 wires. So here are the 2 wires, often called guy wires. The following measurements are indicated on the diagram. Make sure they're all there. CD is 50, GDH. So GDH is 32. HDC is 26. That's in the flat plane. So this is in the standing up triangle, standing up. This is in the flat plane. Be aware of that. And HCD is 80. So this one's in the flat plane as well. Okay. So check that. Find the distance between H and D and the height of the flagpole. All right. Or a vertical pole, just say it's flagpole. Okay, so let's have a look. In triangle HDC, that's this one here. It's another go-between problem. And what can you say? Well, you can say that angle DHC, okay, just come down a bit so you can see this. Not too far here. Okay, so in triangle HDC, hang on, sorry, wrong triangle. Let's go back to the bottom. HDC down here. DHC, so that's that angle, is 180 minus the other 274. Now, why do we do that? I'll just scribble all this out here. Why do we do that? Because we've got the side opposite that. So between those two, we use that angle and that angle. We can use the sine rule. And let's have a look at that in action then. So in that triangle, sine of 80 over HD equals sine 74 over 50. Remember, it's probably preferable to put HD over the sine of 80 equals 50 over the sine of 74. For ease of solving for the unknown, keep it up the top, multiply both sides by sine 80 over here and get approximately 51.225. No rounding off yet until the end. We're not going to do any more with that. So distance from H to D was the first answer, so that's that length, and we can round it to three significant figures. Alright, what about the height here of the pole GH? So we can go into the triangle GHD. That's this, let's tidy this up. GHD is that back triangle, which is standing up there. Okay, so not a bad idea is, I reckon, what they were doing before, GHD, to actually put that in there. And what angle have we got? We said we had the standing up angle, 32 degrees. And we've just found HD is 51. Now, we won't use the rounded off thing. Be careful here, because we're using a subsequent calculation. We don't want to perpetuate a rounding error, so use more figures here. To be accurate to three significant figures, you need at least 4. So we're not going to use 51.2, and therefore we'll go out to more figures. Now we want this side, go to the angle, look out. GH is the opposite. We have the adjacent here because that's the hypotenuse, so we're going to use tan. Tan of 32 is GH over the length, so GH multiplying across by 51.25 is that. So it's approximately 32 metres. So we've been able to, measuring some angles at ground level, work out the height of the pole. Did you realise that? By sighting from ground level. All of this was done at ground level. So that was helpful. Now that's quite useful. You don't have to climb up the pole to see how high it is with a tape measure or anything. Okay, think about the usefulness of this. Okay, come on down to another one, the pyramid problem. A pyramid with a square base, there it is. So this is a square here, 2, 2, 2. It's a right pyramid, so the height here is at right angles to the base, and each side is length 2, and the height of the prism is also 2 centimetres, that one there. So make sure you've got all the data represented on the diagram. We're trying to find the measure of AGF. AGF is in that slopey triangle there, and the total surface area of the pyramid. Okay, so midpoint of GF here, so we're going to create something over here. Let's go down and see it in this diagram here. So the midpoint of GF, there it is, going to be 1 and 1. And then if this is the centre, let's work in this standing up triangle. Okay, so if we do that, then we've got, it's halfway through. C is halfway point. It's a right pyramid, so this is 1 centimetre. And excuse me, ACM is 90. So we should be able to find the length of AM. So hang on, this is this length. Just go back over there. This length here of that triangle. It's another go-between problem. We're going to use this and then use it in this end triangle. So, can we find that? Yes. Pythagoras. So I would rather see Pythagoras in brackets there as the reason. And so if we pull out that triangle AMG now, so that's this triangle sloping in there, what have we just found for it? We just found AMG because that was a go-between value going between the other two. We know this is 1, so because M was the midpoint, and so therefore to find G we got the opposite. We don't have the hypotenuse, so we've got the adjacent. So again it's SOHCAHTOA working with the opposite and the adjacent, so it's the tan of AGM is root 5 on 1. AGM is inverse tan, that was 65.9. So you can say that angle AGM equals angle AGF, or 65.9. So let's go up and look at that. Up here, just go across. So what you're talking about is these two angles would be the same. Alright, what do we have to do? We now have to find the surface area, and the area of triangle AGM, half the product of two sides, sine of the included angle. So we can do that. And then the area of triangle AGF is twice that. And then we've got the base is 2 squared and 4 of these sides. Just go back up and just check that. Or we're saying that the 4 sides are all the same, 4 lateral triangles if you like, and the area of those is half the base times the height in each case. And let's just check that calculation again. We could use sine of the included angle, but what they've used is half base times height. Okay, for each of those, because they had an altitude drawn in there. Alright, so some interesting, more complicated problems there in 3 dimensions. Remember, a useful trick is to extract the triangles because they're in different dimensions there. One's going back through, one might be on the flat surface of the base, and so on. So try and extract the triangles. Alright, let's have a look at another one. Again, same sort of thing. I want to find the measure of ABC, so that's a sloping triangle in there, sloping out this way, and the area of triangle ABC as well. Alright, so definitely a go-between problem. We've got all these sides here of this rectangular box, and so let's use some theorems here to get into this triangle. Well, first of all, this is really isometric drawing. This is really 90. It's a rectangular box, so you can get that by Pythagoras, that thing there. So it's the square root of 7 squared plus 12 squared by Pythagoras. Sorry about that. And we get that. And AB, can we get that as well? Let's have a look. AB, can we get that side? Yes, we know that the height is 5 and this is 7. So again, Pythagoras. And then we can do the same thing with BC. Okay, because they're all in right-angled triangles. It's a rectangular box. So we've got those 3 sides, and then of course we've got the cosine rule. They haven't redrawn it here. We've got this. We're going to get that angle by saying this one was what, 13.892. Don't truncate it because it's going to lead to error. We're going to use these figures again, so you don't want that error perpetuated. So that's what we've got, and we want this angle up here. So the cosine, using the cosine rule, is that, and it's about 77.082 degrees. So 77.1 degrees to 3 significant figures. Alright, study that. Let's have a look now. The area of the triangle, therefore, half the product of 2 sides sine of the included angle, and we've got those sides. And again, using root 74, on the calculator, so you're avoiding truncation of the figures, and that's going to be a more accurate answer. So the area of the triangle is approximately 54.5 centimetres squared. Alright, so the key thing, study it, put all the given information on the given diagram, or make a diagram, then extract the triangles as required to work with. Let's do some problems. So here's question 18 and 19 and 20. Okay, so those are the only problems we've got there. Let's have a look at the solutions. It's going through 18, a bit more. Okay. And then 19. Okay, let's have a look at Pearson's summary of this chapter then, of trigonometry. So here are the first 5 questions, practice questions on the whole chapter. Question 5 there. One of the old exam questions. Okay, let's look at question 6. Okay. Question 7. Again, an old exam question. Question 8. Question 9 and 10. Question 11, question 12, and 13. Let's just see if we can get it all up there. I think it fits on. Not quite. Okay, let's do C and D. Okay, let's look at the solutions to those. Here they are. Question 1 to 4, not the fully worked solutions, just the answers there. 5, 6 and 7. 8 and 9. 10 and 11. 12. 13. 13 is fairly long there. That completes 13. Fairly big problem. Work on that one and see if you can get through it. Well, that's been exciting, hasn't it? The number of applications here that we can use. Now that brings us to the end of that unit on trigonometry. It's been a long one. I hope you feel comfortable with all those skills now. And I'd like to catch up with you in a later presentation on the next topic in this new IB Standard Level course. Cheers for now.